Now we're going to explore diffusion models, which are a type of generative model in machine learning. These models have become very popular because of their ability to generate high-quality data, especially images. Let's explore it in 6 parts. The key components of diffusion models. How does the reverse diffusion process work? What are the main components of a U-Net variant used in diffusion models? What are the differences between forward and reverse diffusion processes? How do time embeddings help in the diffusion process? How does the addition of Gaussian noise affect the image in each time step? For the key components of diffusion models, let's break down the process into manageable parts to understand how they work. The first, forward diffusion process. We start with the forward diffusion process. This is the first step where we gradually add noise to our data. 1. Initial data. We begin with an original data sample, which we'll call x0. 2. Noise. Addition. At each step, some Gaussian noise is added to this data. Mathematically, we represent this. Here, beta t is the noise schedule, and epsilon is sampled from a standard Gaussian distribution. 3. Markov chain. This entire process forms what's called a Markov chain, where each step depends only on the previous step. This makes the process relatively easy to model and understand. 4. Final state. After many steps, t-steps, our data is no longer recognizable. It has turned into pure Gaussian noise. Second, reverse diffusion process. Now let's talk about the reverse diffusion process, which is where the model generates new data. 1. Neural network. A neural network, often a variant of U-Net, is trained to reverse the process we just described. The goal is to start with noise and recover the original data. 2. Inputs and outputs. The neural network takes 2 inputs, the noisy data x sub t and the time step t. It then predicts the noise that was added during the forward process. 3. Denoising. The network subtracts this predicted noise from the data, gradually denoising it step by step until it recovers the original data or generates new realistic data. Third, architecture. The architecture of these models is quite sophisticated. Here's how it generally works. 1. U-Net backbone. A U-Net architecture is typically used, which has 2 main parts. Encoder path. This part downsamples the data. Decoder path. This part upsamples the data. Skip connections. These connect layers from the encoder to the decoder to improve the flow of information. 2. Residual blocks. Both the encoder and decoder often use residual blocks. These blocks help improve the gradient flow during training, making the model more efficient. 3. Attention mechanisms. To capture important details at different resolutions, the model often uses attention modules. These allow the model to focus on the most important parts of the data. 4. Time embeddings. The time step t is encoded as time embeddings, which is similar to the positional encodings used in transformers. This helps the network understand how far along the diffusion process is. 5. Conditional inputs. For conditional generation, like generating images from text, additional inputs, such as text embeddings, can be incorporated using methods like cross-attention. 4th, training process. The training of diffusion models involves objective function and sampling. For objective function, the model is trained to minimize the difference between the predicted noise and the actual noise added during the forward process. For sampling, during inference, the model starts with pure noise and iteratively applies the learned denoising process to generate new samples. 5th, latent diffusion models. There's also a variant called latent diffusion models, which is used in systems like stable diffusion. 1. Encoder-decoder. These models use an autoencoder, often a variational autoencoder, VAE, to compress the data into a lower dimensional latent space. 2. Latent diffusion. Instead of applying diffusion directly in pixel space, the model operates in this lower dimensional latent space, which reduces computational load. 3. Decoding. Once the reverse diffusion process is complete, the model decodes the latent representation back into image space. This method makes it easier to generate high-resolution images while still maintaining the power of the diffusion model. In summary, diffusion models have shown impressive results in generating high-quality, diverse data samples, especially in the realm of image generation. By learning how to gradually denoise data, they have become an essential tool in generative AI, allowing us to model complex data distributions. Now let's dive into the reverse diffusion process, which is key to how diffusion models generate high-quality samples, like images, from random noise. This process is responsible for gradually denoising the noise, turning it into meaningful data. Let's break it down step by step. At its core, the reverse diffusion process is designed to reverse the forward diffusion process. In the forward process, noise is added to data, but in the reverse process, we aim to recover the original data by gradually removing that noise. Mathematically, we're trying to approximate something called the posterior distribution. This represents the probability of getting a less noisy sample xt minus 1, given the more noisy sample xt. First, steps of the reverse diffusion process. 1. Initialization. We start with a pure noise sample, xt, where t is the total number of diffusion steps. This noise is usually drawn from a standard Gaussian distribution. 2. Iterative denoising. The reverse process runs step by step, going from t equals t down to t equals 1. At each step, the model predicts the noise added in the forward process and removes it from the current sample. 3. Neural network prediction. A neural network, usually a U-net architecture, is used to handle this task. The network takes in the noisy sample xt and the time step t as inputs. It outputs an estimate of the noise epsilon, which was added during the forward diffusion. 4. Noise removal. After predicting the noise, the model uses this formula to compute the denoised sample xt1, where beta t is the noise schedule, controlling how much noise is added at each step. Alpha t is the cumulative product of 1 minus beta t over time. Sigma t is a small amount of noise added to keep the process from becoming too deterministic. Z is random Gaussian noise that's added in to help maintain the stochastic nature of the process. 5. Variance prediction. Some advanced models also predict the variance, sigma square, of the reverse process. This helps to fine-tune the sampling, making it more flexible and potentially improving sample quality. Second, key aspects of the reverse process. 1. Stochasticity. The reverse process is stochastic, meaning it involves randomness at each step. This randomness is important because it helps to generate a variety of samples, preventing the model from collapsing to a single mode of output. 2. Guided sampling. For tasks like text-to-image generation, we can guide the reverse diffusion process with extra information, like text embeddings. This can be done by modifying the predicted noise based on the gradients of a classifier or by using mechanisms like cross-attention. 3. Sampling techniques. There are various sampling methods used to improve efficiency and output quality. DDPM, denoising diffusion, implicit models. This technique reduces the number of steps needed, speeding up the sampling process. Ancestral sampling adds more randomness, increasing diversity in the generated samples. 4. Adaptive step sizes. In some implementations, adaptive step sizes are used to balance quality and speed during the reverse process, helping the model generate better samples faster. Third, computational considerations. 1. Memory efficiency. The reverse diffusion process is memory efficient since it only needs to store the current sample and the model parameters. 2. Parallelization. While the reverse process is generally sequential, one step depends on the next. Methods like DDPM allow for some parallelization, which helps with efficiency. 3. Computational cost. The process can still be quite computationally expensive, especially when generating high-resolution outputs or running through many diffusion steps. Fourth, advantages of the reverse diffusion process. 1. High-quality samples. The gradual denoising process allows for the generation of high-quality samples, especially in terms of detail and realism. 2. Flexibility. This process is flexible and can be applied to a variety of generation tasks, including conditional generation, like text-to-image, or even style transfer. 3. Stability. The step-by-step nature of the reverse diffusion process provides stability in both training and sample generation, making it easier to control and improve over time. In summary, the reverse diffusion process is a powerful and flexible approach to generating data. By iteratively refining random noise into structured, meaningful data, it allows us to produce high-quality samples across various domains. The combination of stochasticity, guided sampling, and adaptive techniques makes it a key component in modern generative models. Now we're going to discuss the U-Net variant used in diffusion models. This architecture plays a crucial role in the denoising process, where we transform noisy data back into clean, meaningful data. Let's break down its main components and understand how they work together. First, encoder path. 1. Downsampling blocks. These are layers of convolutions that reduce the spatial dimensions of the input data while increasing the number of feature channels. Essentially, they help the network learn hierarchical representations of the input, making it easier to extract important features at various levels of abstraction. 2. Residual blocks. These blocks are important for ensuring that the network can learn deeper representations without losing useful information. They improve gradient flow, which makes it easier to train deep networks. A key feature of these blocks is the use of skip connections that help retain information across layers. Second, decoder path. 1. Upsampling blocks. These layers do the opposite of the downsampling layers in the encoder. They gradually increase the spatial dimensions of the features to reconstruct the image. Transposed convolutions, or a combination of upsampling followed by convolutions, are often used to expand the feature maps back to their original size. 2. Skip connections. These are direct connections between corresponding levels of the encoder and decoder. Their role is to preserve important fine-grained details that could otherwise be lost during downsampling and upsampling. By passing information directly from the encoder to the decoder, we ensure that the model has all the necessary details to make the denoising process more effective. Third, middle block. This is the section of the network between the encoder and decoder that processes the most compressed representation of the data. The bottleneck may also include additional mechanisms like self-attention, which helps the model focus on the most important parts of the data, even at a global scale. Fourth, additional components. 1. Time embeddings. The diffusion process operates in discrete time steps, and time embeddings are used to encode the current time step into the network. This allows the model to adapt its behavior depending on how much noise has been added during the diffusion process. Essentially, the model learns to adjust its denoising process based on the noise level at each step. 2. Attention mechanisms. Attention layers, such as self-attention or cross-attention, are added to the U-Net at higher resolutions or in the bottleneck. These mechanisms allow the model to capture global context, meaning the model can focus on distant parts of the image when making predictions, improving the quality of the generated output. 3. Normalization layers. Group normalization or layer normalization are used throughout the network. These layers help stabilize training, making the model more robust and faster to converge. 4. Activation functions. To introduce nonlinearity into the network, modern U-Net architectures often use SciLU, also known as Swish, as the activation function. This helps the model learn complex patterns more effectively. 5. Final output layer. The final layer is typically a convolutional layer that outputs the denoised image with the same spatial dimensions as the input. It predicts the noise to be removed, which is the crucial step in the denoising process of diffusion models. 5th, Flexibility and efficiency. The U-Net variant used in diffusion models is designed to be both flexible and efficient. Its architecture allows the model to capture both local features through downsampling and upsampling, and global context through attention mechanisms. This makes it particularly well suited for tasks like image generation, where preserving both fine details and the overall structure is important. In summary, this U-Net variant helps the model effectively denoise and generate high-quality images by using a combination of downsampling, upsampling, skip connections, and attention mechanisms. The time embeddings and normalization layers further contribute to the model's stability and efficiency. Now let's compare and contrast the forward and reverse diffusion processes in diffusion models. Both are crucial to how these models work, but they serve very different purposes. Understanding their main differences will give us a clearer picture of how diffusion models operate. 1. Purpose. For forward diffusion. This process gradually adds noise to the original data. It transforms complex data distributions, like an image or sound, into simple Gaussian noise. It's used during training to create noisy versions of the input data, so the model can learn how to denoise it. For reverse diffusion. In contrast, reverse diffusion gradually removes noise from a noisy input. It transforms Gaussian noise back into complex data distributions. This process happens during inference, when the model is generating new samples. 2. Direction. For forward diffusion. It moves from clean data to pure noise. You start with something detailed, like an image, and slowly degrade it into random noise. This process runs from t equals 0, starting with clean data, to t equals t, where t is the total number of diffusion steps. For reverse diffusion, the reverse process goes in the opposite direction. It moves from pure noise to clean data. It runs from t equals t, where you start with pure noise, to t equals 0, where the goal is to restore the data to its original state. 3. Process nature. For forward diffusion, this is a deterministic process. If you know the noise schedule, how much noise you add at each step, you can compute the process exactly without any randomness. It's mathematically straightforward and doesn't require a neural network. For reverse diffusion, the reverse process is stochastic, meaning it involves some randomness at each step. To carry out reverse diffusion, you need a neural network, usually a U-Net variant, to approximate the denoising steps and predict the noise that was originally added. 4. Complexity. For forward diffusion, it's relatively simple. At each step, you just add some Gaussian noise to the data, and this can be described with a simple mathematical formula. For reverse diffusion, this is more complex because it involves a neural network that predicts the noise at each step. It requires sophisticated architectures, like the U-Net, to perform the denoising at each step of the reverse process. 5. Training and inference. For forward diffusion, it's mainly used during the training phase, generates noisy samples for the model to learn from. For reverse diffusion, it's used during inference, or generation, produces the final output samples. 6. Mathematical formulation. For forward diffusion, this process is described by the equation, where beta t is the noise schedule and epsilon is Gaussian noise. This equation shows how each step adds a bit of noise to the data. 7. Flexibility. For forward diffusion, the forward diffusion process is typically fixed once the noise schedule is set. It doesn't change once you've defined how much noise to add at each step. For reverse diffusion, the reverse diffusion process is more flexible. For example, it can be adapted for conditional generation, like generating an image from a text description. It also supports techniques like guided sampling or classifier-free guidance to help control the output. 8. Computational requirements. For forward diffusion, it's relatively computationally lightweight. You don't need much processing power to add noise to data, so it can be pre-computed or done on the fly. For reverse diffusion, this process is computationally intensive. It requires multiple forward passes through a neural network for each step, especially when you're generating high-quality or high-resolution samples. So, to summarize the key differences, the forward diffusion process is used for training the model, where it gradually adds noise to the data, turning it from complex data into simple Gaussian noise. The reverse diffusion process is used during inference, where it takes pure noise and, using a learned neural network, gradually denoises it into meaningful, complex data. These two processes work together, with the forward diffusion creating the noisy data that the model learns from, and the reverse diffusion using that learned knowledge to generate high-quality, clean samples. Now, let's talk about time embeddings and their role in diffusion models, particularly in how they help the model understand and manage the denoising process across different stages. First, temporal awareness. Time embeddings give the model temporal awareness, which means the model can recognize the different stages of the diffusion process. This is important because, 1. The model can adjust its behavior based on how much noise is present at each time step in the process. 2. It helps the model decide whether to add more noise or remove noise, depending on where it is in the sequence of steps. Second, noise prediction. Time embeddings also play a crucial role in noise prediction. 1. They allow the model to accurately predict how much noise is in the image at a given time step. 2. The model can then adapt its denoising strategy based on the noise level expected at that particular stage in the process. Third, architecture integration. In terms of how time embeddings are integrated into the model's architecture. 1. Time embeddings are usually added to the input of residual blocks within the UNet architecture. These are important layers that help the model process and adjust its predictions. 2. The embeddings are processed through trainable linear layers to help scale and shift the operations in the residual blocks, enabling the model to adjust to different stages of the denoising process. 3. In more advanced implementations, time embeddings are applied to the dense weights and attention blocks. Techniques like time LoRa can be used to enhance this application and improve model performance. Fourth, encoding method. To create these time embeddings, a common approach is to use sinusoidal encoding, which is similar to what's used for positional encoding in transformer models. 1. This encoding maps each time step, t, to a vector, allowing the model to distinguish between the various stages of the diffusion process. 2. Essentially, the model uses this encoding to understand where it is in the process and how the noise should be treated at each step. Fifth, performance improvement. Incorporating time embeddings has been shown to improve the performance of diffusion models. Here's how. 1. They help the model adapt over time, which is important because the data can change in unpredictable ways. This adaptability helps the model handle the challenges posed by non-stationarity, meaning that the distribution of data can shift over time. 2. When combined with techniques like time LoRa, time embeddings can offer even better performance than when used alone, allowing the model to produce higher quality outputs. In summary, by providing temporal context, time embeddings help the model navigate the denoising process, ensuring that it can gradually refine the data from noise to a coherent, high-quality output. They are an essential tool for guiding the model through the complex task of generating clean data from noisy inputs. Now, let's break down how the addition of Gaussian noise in diffusion models works and how it affects the image at each time step. First, gradual corruption. 1. Stepwise noise addition. At every time step in the forward diffusion process, a small amount of Gaussian noise is added to the image. This noise gradually corrupts the original image. 2. Increasing corruption. As the time steps progress, the image becomes more and more corrupted. By the end of the process, the image will have shifted completely from its original data distribution to something that resembles pure Gaussian noise. Second, noise schedule. 1. Controlled variance. The amount of noise added at each time step is controlled by a variance schedule, denoted by beta t. This schedule dictates how much noise is introduced at each step. 2. Increasing noise levels. The noise level generally increases with each time step. In practice, beta t usually starts at a very small value, for example 0.0001, and increases as the process continues, often reaching values like 0.02 at the final step. This ensures that the image becomes progressively more noisy over time. Third, mathematical representation. The process of adding noise can be mathematically represented by the equation, where xt is the image at time step t, beta t is the noise level at time step t, eta t is a Gaussian random variable, which adds the actual noise at each step. Fourth, effects on image distribution. 1. Gaussian transformation. The repeated addition of Gaussian noise transforms the image's distribution towards a pure Gaussian distribution as the process progresses. 2. Markov chain. This noise addition process forms a Markov chain, where each noisy image at a given time step depends only on the image from the previous time step. This structure simplifies the modeling process and makes it more predictable. Fifth, preservation of structure. 1. Early time steps. During the initial steps, the noise is minimal. This means the original structure of the image is mostly preserved, and the image still looks fairly recognizable. 2. Later time steps. As the time steps progress, the image becomes progressively blurred and loses its original features. By the end of the process, it's almost entirely noise. Sixth, theoretical implications. 1. No clipping. Unlike traditional image processing, the noisy values of the image are not clipped to standard pixel value ranges, like 0 to 255. This allows the model to work with true Gaussian noise, which helps preserve the distribution properties of the noise. 2. Continuous space. By not restricting the values to discrete pixel ranges, the diffusion process can operate in a continuous space, which is beneficial for learning and generating complex data distributions. In summary, by carefully controlling how Gaussian noise is added over time, diffusion models can effectively reverse this corruption during the reverse diffusion process. This enables the generation of high-quality images from pure noise, showcasing the power and flexibility of diffusion models in tasks like image synthesis.